So let's begin the lecture 7.4, improper integrals. You're familiar with the concept of definite integrals. And definite integral is an integral like this, f of x dx from a to b, and geometrically, especially if you're dealing with a positive function f of x, that's going to be this area here, the area under the curve f of x above the x-axis and between the two vertical lines x equal a and x equal b. And since a and b are finite numbers, this is called a proper integral. Now, what is an improper integral? An improper integral is a situation where either a or b or both of them are infinity. Like, for example, if you have some function f of x and you want to know integral from a to infinity, so the area under the curve above the x-axis from a vertical line a up to infinity, or if you have integral from negative infinity up to b of f of x dx, or if you have integral from negative infinity to positive infinity f of x dx, these would be called improper integrals. So the definition of an improper integral is an integral where at least one of the two bounds is not finite. It's either infinity or minus infinity. Now, you have no problem with this. You already know that. So let's take a look at this example here from the book. So if you have the function f of x is equal 1 over x squared, if I ask you to find the area under the curve, 1 over x squared, so that's the area under the red curve above the x-axis between the numbers 1 and 2. So the bounds are 1 and 2. I'm asking you to find this 1 over x squared dx, and the bounds of the integral are from 1 to 2. So this area here. Then you just need an antiderivative of that. This is like from 1 to 2, x2 minus 2 dx. And the antiderivative of this is going to be 1 over minus 1, x2 minus 1, from 1 to 2. If I simplify that, I get negative 1 over x. From 1 to 2, I need to plug in 2 first. I get negative 1 over 2, minus, then I plug in 1, I get negative 1 over 1. So that's going to be negative 1 over 2 plus 1. That's 1 over 2, and that's it. I found the answer. And that would be a definite integral. What if I'm interested in integral from 1 to infinity of 1 over x squared dx? So the approach we're going to take for that is, rather than calculating this integral, we're going to calculate integral from 1 to b, 1 over x squared dx. And then we're going to see what happens if we increase b. So here b is 2, then b could be 3, then it could be 4. So if I just make this smaller so that you can see, then it could be 4, then it could be 5. And every time I'm increasing b, I get a better approximation of this area, this unbounded area from 1 to infinity. So if x is 2, yes, I get an approximation which is not very good, because I can see here that this area is not counted. But if I increase b, so go to 3 and then to 4 and then to 5, you can see that this approximation is going to get pretty good, especially because this is a decreasing function, and then after a certain point the area under the curve is going to be negligible. Yes, so let's try that. This is going to be negative 1 over x from 1 to b. So if I plug in 1, I get 1 over, if I plug in b, I get negative 1 over b. And if I plug in 1, I get minus 1. So it's going to be 1 minus 1 over b, if I simplify that. So if b is 3, I'm going to get 1 minus 1 over 3. If b is 4, I'm going to get 1 minus 1 over 4. If b is 5, I'm going to get 1 minus 1 over 5, and so on. So how can I improve that approximation? Obviously by increasing b. But the question is, why can't I just increase b to infinity? How do I do that? I can easily take the limit of this as b approaches infinity. So I'm going to keep this so that you can ask questions if you have any. So in order to calculate integral from 1 to infinity of 1 over x squared dx, I can calculate integral from 1 to b of 1 over x squared dx, and then take the limit of that as b approaches infinity. So since I calculated this one already, integral from 1 to b of 1 over x squared dx, I found it to be 1 minus 1 over b. So this is going to be limit as b approaches infinity of 1 minus 1 over b. And it's evident that if I increase b, this part is going to approach 0. So I get 1 minus 0, which is 1. So the exact area under this curve from 1 up to infinity, I'm going to get rid of this blue line, from 1 up to infinity. So the whole area, which is an unbounded area, is going to be a finite number 1. Is the approach clear, how we're going to approach this type of integral, improper integrals?
Yeah.
Great. Okay, so this is the same example in the book. So you calculate integral from 1 to b, and you're going to get 1 minus 1 over b, which is the same thing as what we have here, negative 1 over b plus 1. And then if you plug in, for example, 10, you're going to get 1 minus 1 over 10, 0.9, 100, 0.99, 1000, 0.999. And then it's clear that by increasing b, the whole area is going to approach 1. And of course, if you take the limit of that part as b approaches infinity, you get 1. So generally, we have this definition here for improper integrals. So this is an integral where the upper bound is infinity and the lower bound is a finite number a. Improper integral of f over an interval from a to infinity. If f is a continuous function on the unbounded interval from a to infinity, then the improper integral f over this unbounded interval from a to infinity is defined to be, so this area here from a to infinity is going to be the limit as b approaches infinity of this ordinary definite integral. So let's take a look at another example. It's not always the case that that area is going to be bounded. So sometimes that area is infinity. And this is what we're going to see in the next example. So if I give you this problem, find the value of this improper integral from 2 to infinity of 1 over x dx, which is basically the area under the curve 1 over x from 2 to infinity. If I want to graph it, it's going to be like this. So the red curve is the 1 over x curve, and then x equals 2 is this green line here. So we're interested in this area under the curve. So this area from here all the way up to infinity. Let's see what happens if I do that. According to the definition, this is going to be limit as b approaches infinity of integral from 2 to b of 1 over x dx. So I'm replacing infinity here with b, and then I calculate this thing here. This is going to be something in terms of b. It's going to be a function in terms of b. It's going to depend on b. And then I take the limit of that function as b approaches infinity. So I know this part here is going to be, I'm going to do it over here. The antiderivative of ln of 1 over x is ln of x, of ln of absolute value of x, and then it's from 2 to b. So it's going to be ln of b minus ln of 2. And b is going to be positive, greater than 2, so I don't bother with the absolute value. So this is going to be limit as b approaches infinity of this function here in terms of b, ln of b minus ln of 2. So we discussed the shape of ln of x. We know that as x approaches infinity, ln of x is an increasing function which is going to approach to infinity. So this is going to be infinity minus ln of 2, which is going to be infinity. So you see, this area indicated here, it's not a finite area. This area is going to be infinity. So with the previous example, when we calculated the area under 1 over x squared, we got a finite number, 1. The whole area was just 1. But if we have 1 over x, then this area is going to be infinity. Do we understand this second example? Any questions? Okay, so let's take a look at this third one.
Oh, sir, I have just a question. So ln infinite is infinite?
Yeah, because ln of x looks like this. It's a function with a domain of only positive numbers. That's y equals ln of x. And it behaves like this. Y is going to approach infinity as x approaches infinity, and y is going to approach negative infinity as x approaches 0 from the right. Yes. So if you take the limit of ln of x as x approaches infinity, so you can see what happens. It's going to continue like this. Yes. So as x gets bigger, y also gets bigger, and it approaches infinity. But if you take the limit of ln of x as x approaches 0 from the right, that is if you're here, and x approaches 0 from the right, what happens to the y value? It's going to go down to negative infinity. Make sense?
So ln what is equals to minus infinite?
ln of what is equal? No, there's no, you cannot say that a function is equal minus infinity. Minus infinity or infinity, these are not numbers. Yes? So we cannot say ln of what? Limit of this function as x approaches 0 from the right is minus infinity. What does that mean? That means if you plug in numbers that are close to 0, but positive. So for example, if you plug in some numbers like this, 0.1, because 0.1 is positive, but very close to 0. You get closer, 0.01, and then 0.001, and then 0.0001. And if you keep doing that, yes, that's the meaning of approach. That means x approaches 0 from the right. And you can just grab your calculator and try that. What happens if you calculate ln of 0.1, and then ln of 0.01, and then ln of 0.01, and then keep doing that. Then the y values are going to keep decreasing and going down to minus infinity. So that's the meaning of approach. As x gets closer and closer to 0, that's what you can see here in this diagram. As x gets closer and closer to 0, the y values, they're going to get close, they're going to decrease without bounds. They're going to go to negative infinity. So I can give you some examples of that. If I just draw the ln of x, so let's just take a look at the values. You see these numbers, if you look at the x coordinate is getting closer and closer to 0 now, yes? What happens to the y coordinate? Yes, it gets closer and closer to negative infinity. And I can do that forever, yes? So here I have a number that's, yeah, after a certain point, there is a calculation limit here, so it doesn't give me the numbers anymore, but you get the idea, right?
Yes, I understand now.
The values that are closer to 0, the x values that are closer to 0, they give outputs that get a smaller and a smaller and a smaller, and generally they go down to infinity, to negative infinity. And what happens if x approaches infinity? As x gets bigger, y also gets bigger. Make sense?
All right.
Okay, so let's take a look at the next example. Find the area of the region under the region R under the curve y equals e to the power of minus x over 2 for x's that are greater than 0. So basically, we want to know this. Integral from 0 to infinity of e to the power of minus x over 2. So the area of the region R under this curve, that's our function, for the values of x that are greater than 0. And you can see that there is no upper bound. So the upper bound is going to be infinity. So what do? We're going to write this in terms of a limit. We replace this infinity here with b. We calculate the area from 0 to b of e to the power of minus x over 2. And then this here is going to be a function in terms of b. It's going to depend on b. And then we take the limit of that as b approaches infinity. So I'm going to first calculate this one because that's a definite integral which we already know how to handle. And then I'm going to replace whatever I have here with that function in terms of b and take the limit. So integral from 0 to b of e to minus x over 2 dx. I can do that by doing a substitution. Let's take u to be minus x over 2. Then du is going to be minus 1 over 2 dx. And I can see that what I need is a minus 1 over 2. So I'm going to multiply by a minus 1 over 2 and then divide by a minus 1 over 2. At the same time, I'm going to change the bounds of the integral. So if x goes from 0 to b, what happens to u? U is going to, if I plug in 0, I get 0. If I plug in b, I get negative b over 2. So in order to create my du, I need a negative 1 over 2, which I'm going to multiply here. And then in order to cancel this, I'm going to multiply by negative 2 outside. And now I'm ready to do the substitution. It's going to be negative 2 integral of e to u du. So e to the power of u, and then the rest is going to be du, from 0 to negative b over 2. The antiderivative of e to u I know is e to u, so it's going to be negative 2 e to u from 0 to negative b over 2. And at this point, if I plug in values, I get negative 2 e to the power of negative b over 2 minus, if I plug in 0 into this, I get e to the power of 0, that's 1. Let me just write this completely. I get negative 2 e to the power of 0. So it's going to be negative 2 e to the power of negative b over 2. This is going to be just 2. Yes, because negative, this is just 1, and negative, negative, positive, so plus 2. So this is the value of this improper integral over here, and I can just replace this with this expression here in terms of b. So if I do that, I'm going to get this limit here. And let's just try to calculate this limit. So it's going to be limit of 2 minus 2e to the power of negative b over 2 as b approaches infinity. So this is going to be, if I just replace b with infinity, I get 2 minus 2e to the power of negative infinity divided by 2, which is negative infinity. Yes, and this is going to be 0. So the answer is 2. So why is that the case? Because look, what happens if I have e to the power of negative infinity, which is the same thing as having 1 over e to infinity. Yes. So you agree that e to infinity is a very, very big number. And if you have a fraction and the denominator gets bigger and bigger, what happens to the whole fraction? The whole fraction approaches 0. So e to negative infinity is 0. 0 times 2 is 0. So 2 minus 0 is just 2. So that area is going to be exactly 2. So very quickly, what I did was I want to calculate area from 0 to b of e to the power of negative x over 2 dx, to infinity. I write that as a limit. I replace this infinity here with b. And then b approaches infinity. This here is a simple definite integral which can be done by a substitution. And if I do so, I'm going to get limit as b approaches infinity of 2 minus 2e to the power of negative b over 2. And then in order to calculate this, I just need direct substitution. That is, I plug in infinity into this, I get e to the power of negative infinity. E to the power of negative infinity is like 1 over e to infinity, so it's 0. So this, the whole thing is going to be 0. I get 2 minus 0 is equal to 1 over infinity. Are we good? Any questions? Okay, so what do we do if we have an improper integral in the form from negative infinity up to a certain number b? So if you have integral from negative infinity up to a certain number b, f of x dx, we're going to use the same approach. In this case, we're going to replace negative infinity with a. So it's going to be integral from a to b of f of x dx. And then we take the limit of this as a approaches minus infinity. So we have this definition here: improper integral over an unbounded interval from negative infinity to b. If f is a continuous function of an unbounded interval from negative infinity to b, then the improper integral of f over this interval is going to be defined like this. So we replace minus infinity with a, Now we're dealing with an ordinary definite integral, which we can calculate in terms of a. And then we take the limit of that definite integral as a approaches negative infinity. So let's use it for this example here. Find the area of the region R bounded above by the x-axis and below by the curve y equals minus e to 2x. So basically we are looking for we're looking for this area, which is an unbounded area. On the right, it's bounded to x equal 1, but on the left, it's unbounded, so it goes to negative infinity. So we're looking for, and since it's an area below the x-axis, yes, it's going to be, the integral is going to be a negative number. But the area is positive. The area is always positive, and the way you get the area is by doing the function on top minus the function at the bottom. So in this case, the function on top is going to be the x-axis, and the formula for the x-axis is y equals 0. So you can think of these two functions. You can think of the function y equals 0, which is basically the x-axis, and this function, which is the blue curve here, and you're looking for the area between these two functions from negative infinity to 1. And of course, you're going to do the curve or the function on top minus the 1 at the bottom. In this case, this one is on top. So it's going to be integral from negative infinity up to 1 of the one that's on top, 0, minus the one that's at the bottom, minus e to the power of 2x dx. You're looking for this. Is that clear?
So just a question.
Yes.
Okay, if we did it in a different order, is it the same as we did before? Just take the absolute value.
You would get the negative value, and then you take the absolute value, of course. Yes.
Oh, okay, thank you.
So this is going to be the same as integral from negative infinity to 1 of e to the power of 2x dx, which I'm going to solve in terms of a limit. It's going to be limit integral from a to 1 of e to the power of 2x dx, and now take the limit of this as a approaches minus infinity. So I'm going to do this and then replace the definite integral with whatever the value of its integral is. So from a to 1 of e to the power of 2x dx. It's again a simple substitution. I'm sure you can do it on your own. It's going to be 1 over 2 e to the power of 2x from a to 1. So it's going to be 1 over 2 e to the power of 2 minus 1 over 2 e to the power of 2a. Very good. So at this point, I can replace this here with the value. I take the limit. So the answer is going to be limit as a approaches minus infinity of 1 over 2 e to 2 minus 1 over 2 e to the power of 2a. It's going to be. So what happens if I plug in negative infinity for a here? If I plug in negative infinity, I get e to the power of 2 times negative infinity. 2 times negative infinity is negative infinity. So it's e to the power of negative infinity. Just like the previous example that I showed you, e to negative infinity can be replaced with 0 because it's like having 1 over e to infinity. So this is going to be, the whole thing is going to be 0. I get 1 over 2 e to the power of 2. Do we understand the limit? Is it clear for everybody why this is the case? If I have limit of e to the power of x as x approaches negative infinity, that's going to be 0. Yes. Why is that the case? Because it's like having e to the power of negative infinity, which is 1 over e to infinity. That's gigantic. So 1 over a number that increases to infinity, that's going to approach 0. So it's same story here. When you replace this a here with minus infinity, this part here is going to approach 0. Because a approaches negative infinity, 2 times negative infinity is negative infinity, e to negative infinity is 0, so the whole limit here is going to be 0. You get 1 over 2 e to the power of 2. Any questions?
I have one, please.
Yes, go ahead.
So in the question, they gave us the y and x equals 1. How did we get y equals 0? I got messed up here.
Oh, we were looking for the area. Yes, we were. If imagine if the question is asking you for something like this: find this improper integral from negative infinity to a certain number, let's say 1 f of x dx. Yes. Then the only thing you need to do, you need to write this in terms of a limit integral from a to 1 f of x dx. As a approaches minus infinity, first you get this, you replace whatever you have here with the value of the integral, and you take the limit. Yes, and you're done. But in this problem, we're not asked for an improper integral, we're asked for an area. So it says find the area of the region R that is bounded by the x-axis. That's how you get y equals 0, because y equals 0 is the formula. It's a horizontal line for x-axis. So it's the area between the x-axis and the curve y equals e to minus 2x. So we know that the area between two functions f of x and g of x is going to be integral from a to b of f of x minus g of x dx if from a to b f of x is on top and g of x is at the bottom. Remember that? Same story here. When you look at this curve, you can see that the x-axis is on top and the curve, the blue curve, is at the bottom. So we have to do the one that's on top, the x-axis, minus the one that's at the bottom. So we get integral from negative infinity to 1 of 0 minus, so the function is negative, minus e to negative 2x dx, which is going to be integral from negative infinity to 1 of e to negative 2x dx. It's not negative, positive, sorry. Make sense?
Yeah, it's clear now. Thank you.
Sure. Okay, so now what do you do if you have an improper integral where both bounds are unlimited? So you have integral from negative infinity to infinity of f of x dx. So what you do is you're going to use this. We know that this is one of the properties of integral. If you have an integral from a to b of f of x dx, this is integral from a to c of f of x dx plus integral from c to b of f of x dx. So this integral can be broken into two integrals. Integral from negative infinity to some c f of x dx plus integral from c to infinity of f of x dx. And then this one can be solved in terms of a limit. This one can also be solved in terms of a limit, as we saw examples, and then you add them up. And of course, if one of these two limits do not exist, if one of them is infinity, then we don't even bother with the other one. So if you calculate this first one and you get this is infinity, then you don't need to bother with the next one. That wouldn't matter. You would say that the integral, the improper integral, diverges. So when this is infinity, you say that the improper integral diverges. Like the example we did with the function f of x equals 1 over x, when we calculated integral from 1 to infinity of this, we got limit of integral from 1 to b of 1 over x dx. This, as b approaches infinity, this turned out to be ln of b. Oops, what's going on? Just do it again. So for the function f of x is 1 over x. Integral from 1 to infinity of 1 over x dx. For this one, we wrote that in terms of a limit. Integral from 1 to b of 1 over x dx as b approaches infinity. And what we got for this one was ln of b minus ln of 1. So this is going to be limit of ln of b minus ln of 1 as b approaches infinity. And we learned that ln of b as b approaches infinity is infinity. So this is going to be, and this is just 0. So it's infinity minus 0 is equal to infinity. So in situations like this, I think I forgot to mention that over there, you say that the improper integral is divergent. It diverges to infinity. It doesn't converge into a finite number. So for a problem like this, if the first integral or the second one, if any of the two diverges to infinity, you say that the integral, the improper integral is divergent. So let's just read this quickly. Let f be a continuous function over the unbounded interval from negative infinity to infinity. Let c be any real number. And usually we take c to be 0. That makes things easier to take c to be 0. Then suppose that this one and this one, both of them, are convergent. That means if this is a finite number and this one is also a finite number, then you would say that the integral from negative infinity to infinity of f of x dx is the sum of these two. If one of them diverges, then you can say that the whole improper integral diverges. So let's take a look at one example. Integral from negative infinity to infinity of x e to the power of minus x squared dx. So first we're going to break that into two improper integrals from negative infinity up to 0, x e to minus x squared dx, plus integral from 0 to infinity of x e to minus x squared dx. Yeah, so it's usually easier to take c. I could use 1 for here. I could use 1, 1. I could use 10, 10. Doesn't matter. Any c, any real number. But it would be easier if I just use 0. Now, let's do this one first. Integral from 0 to infinity of x e to the power of minus x squared dx is going to be written as limit of integral from 0 to b of x e to the power of minus x squared dx as b approaches infinity. Now, I'm going to do this first and then replace it with its value. So 0 to b of x e to minus x squared dx. This is going to be a simple substitution. Let's just do that quickly. If I take u to be negative x squared, then du is going to be minus 2x. I'm missing the minus 2, so I multiply by a minus 2 and divide by a minus 2 outside. So this is going to be negative 1 over 2 integral of e to u du. And if u is minus x squared, then u is going to change from plug in 0 here, you get 0, to b. If I plug in b here, I get minus b squared. So from 0 to minus b squared. Everyone's following?
Yes.
So minus 2 over b e to the power of minus b squared minus 1 over 2 e to the power of 0. So I know that the antiderivative of e to u is simply e to u. So using the fundamental theorem, if I plug in minus b squared, I get this. And if I plug in 0, I get this. So this is going to be limit as b approaches infinity of, this is simply 1 times negative 1 over 2, negative 1 over 2, negative, negative, positive. So we get 1 over 2 minus 1 over 2 e to the power of negative b squared. So same story, as b approaches infinity, b squared is going to approach infinity. So negative b squared is going to approach negative infinity, and e to negative infinity is going to be 0. So this part is going to just be 0, and you get 1 over 2. So if you do the other one using the same method, as you can see here, for that one, you're going to get negative 1 over 2. So let's just go over the other integral. So I did the second one, and here's the first one. Integral from negative infinity to 0 of x e to the power of negative x squared. You can write that as in terms of a limit, a to negative infinity, a from a to 0. Then you take the antiderivative of this. Antiderivative of this is going to be negative 1 over 2 e to negative x squared from a to 0. You plug in 0, you get negative 1 over 2. You plug in a, you get negative 1 over 2 e to negative a squared. And now if a approaches negative infinity, a squared is going to approach infinity. So this is probably too small. Okay. So as a approaches negative infinity, a squared is going to approach infinity, because even a negative number squared is going to be positive. So negative infinity squared is going to be positive infinity, but then you have a negative here. So negative infinity, and then you have e to the power of negative infinity, which is 0. So you get negative 1 over 2. So this one turns out to be negative 1 over 2 and this one turns out to be 1 over 2. And if you add them up, you get 0. So this is the one that I did on the board. You get 1 over 2. And then when you add them up, you get negative 1 over 2 and 1 over 2 is 0. And if you graph this, you will see that it's going to be a function that is symmetric with respect to the origin. So this first one, integral from negative infinity to 0, would be the actually it would be the negative of the area of the region 1. So region 1 is 1 over 2, and since it's below the x-axis, the integral is going to be negative 1 over 2. And the second integral from 0 to infinity is going to be the area of this region, which is 1 over 2. And the integral is going to be the net area. That is, areas above the x-axis are positive, areas below the x-axis are negative. So it's going to be 1 over 2 plus negative 1 over 2 gives you 0.
I have a question.
Yeah, go ahead.
Could we do the antiderivative before breaking it down into two functions, like you did?
That's actually a very good idea. You can do that. Yeah, so you say, I have x e to the power of minus x squared dx. Let's just forget about the bound. Just do that as an indefinite integral. I take u to be minus x squared. Du is going to be minus 2x dx. Multiply by minus 2, divide by minus 2. This is going to be negative 1 over 2. Integral of e to u du. So it's going to be negative 1 over 2 e to whatever u is, minus x squared plus c. Yes, and then you don't need to change the bounds anymore. Yes, you can keep the bounds because you're not working with u, you're working with x. Did I answer your question?
Yeah.
Okay. So yeah, I explained this one. Yeah, that's it. Is there any other example? So what is this here? And more explanations about the same example. Okay, so let's just work on one of the problems from web work, and then I'm going to let you start working on the rest of the problems from 7.4. So this first one is 1 over x squared. That was one of the examples we did in the book. Let's do this one. Integral from 7 to infinity of ln of x over x dx. So as you suggested, I'm going to just first take care of this as an indefinite integral. I take u to be ln of x, and then du is going to be 1 over x dx. So this is going to be integral of u du, which is going to be 1 over 2 u squared plus c. Replacing u with whatever u is, you get ln of x squared plus c. So now you can use this as the antiderivative. So when I calculate integral from 7 to b of ln of x over x dx, this is going to be 1 over 2 ln of x squared from 7 to b. So that's going to be 1 over 2, which I can factor out, ln of b squared minus ln of 7 squared. Yes, so that would be the definite integral from 7 to b, and this integral here is going to be the limit of this as b approaches infinity. So it's going to be the limit of 1 over 2 ln of b squared minus ln of 7 squared as b approaches infinity, right? But I know that ln of infinity is infinity. So this one is going to be infinity minus ln of 7 to the power of 2. Infinity minus a finite number. That's going to be infinity. So this is not convergent. It's divergent. So it says that determine whether the integral is divergent or convergent. Since this limit is infinity, this is divergent. If it's convergent, evaluate it. If not, state that it's divergent. So I'm just going to copy divergent here, paste it here, submit the answer, and that's the way to go. So if the answer is infinity, you just say that the improper integral is divergent. You're good?
When we're talking about the limit, it's like talking about the area, right?
The limit, we are calculating, basically we are trying to calculate an area, but sometimes, and that area is expressed in terms of a limit. And if that limit exists, if it's a finite number, then we know that that area is equal to that finite number. So for example, if this limit is 10, you would say this infinite area, this area which is actually open on one side, has a finite surface. Yes. So, but if it's infinity, then it means that that area doesn't have a finite surface.
Okay.
So you say that the integral is the improper integral is divergent.
Okay, thank you.
So it's actually interesting that if you have an area under a curve, like for example, the curve 1 over x squared, let's say from x equal 1 all the way to infinity. Yes, this is open here. It never ends. And this curve never touches the x-axis. So this surface here, this area here is unbounded. Yes, yet it has a finite area. And that area, as we calculated for this one, is going to be 1. But sometimes, like in this example that I just showed you, the area is not going to be convergent into a finite number. So the only thing you need to do here is say that it doesn't converge, it's divergent. Okay.